Alright, so we have this problem where we have to find f prime, and so this is one of those problems where you're like, oh, I was only assigned one problem, and then you look at it and it's like parts A through J, and you're just like, ugh. But this isn't too bad. Um, yeah, so, well, then again, these problems are actually kind of tedious because, oh, that's a different color than I usually have. Let's go back and change that. I was doing some stuff where I was using different colors, but now I'm not doing that. Okay, so first of all, we have f of x, y, z equals x to the y. And so one of the, like at the very end of the section, they sort of tell us how we need to do these types of problems. And essentially what we need to do is we need to write all of these functions in terms of addition, multiplication, exponentiation, etc. But also, and also compositions, but also in terms of projections. So whenever we see x, we think of that as pi 1 of x, y, z. So really what this is this is pi 1 of x, y, z being raised to the power, I'll just write this, being raised to the power of pi 2 of x, y, z. And moving forward, I'm not going to write x, y, z every single time, or if it's in two variables, I'm not going to write x, y every single time. I'll just write pi 1 to the power of pi 2, and so anytime I write pi 1, it'll be implied that I mean pi 1 of x, y, z, or whatever it is. Now, recall that, okay, so I don't want to use, okay, so we're going to let y be some function. So if y of x is a function which is defined by, okay, so what do? We take, let's just call it g and h. So g of x, some function g of x to the power of another function h of x. Then we can evaluate this using standard, calculus. So, but it's not just standard calculus, so you have to remember what technique we use here. And so here what we need to use is logarithmic differentiation. So the first thing we do is we take the natural log of both sides. So we have natural log of y is going to be equal to the natural log of g to the x to the power of h of x. And then because this is a natural log, we can bring the h down in front. So this is just h of x times the natural log of g of x. And now we can take the derivative on both sides. So the derivative of the natural log of y equals the derivative of h of x times the natural log of g of x. So on the left-hand side, if we use a chain rule, this becomes 1 over y times dy dx. Or I'm just going to write y prime for dy dx. And that's going to equal, let's see, so we get, let's see here. So we get h prime of x times natural log of g of x. And then we have to add, well, first we take the derivative of the natural log of g of x. So by the chain rule, that's going to be, well, derivative of natural log is 1 over the thing. So we're going to get 1 over g of x times g prime of x. So we'll end up with g, what? Right, so we'll have h of x over g of x times g prime of x. Yes. And so then we move the y over to the other side, and we get y prime equals y times h prime of x times the natural log of g of x plus h of x over g of x times g prime of x. And so then we finally replace y with what we started with. So y equals g to the power of h. So y prime equals g to the power of h. And this whole thing is multiplied by h prime, natural log of g of x, plus h over g, g prime. And we use this equation like all the time in this problem. Okay, so the f that we're starting with is equal to pi 1 to the power of pi 2. So, let's see here. F prime equals, and the other thing is, note that everything that I did here is in the one. Normally you'd think of x as being like one-dimensional, or like a one-dimensional variable. Everything that I did here would hold in multiple dimensions. Does that make sense? Yeah, but the only thing is you would need to, if you're doing this in multiple dimensions, you do need to keep a few things in mind, like, for example, 1 over, if you're plugging in x and x is multidimensional, then, like if you're taking natural log of a vector, that's just taking natural log of each of the individual coordinates. So you'd have to do things like that, but you can make it work. So anyways, if f is pi 1 to the power of pi 2, then f prime is, let's see here, so we start with y, which here is pi 1 to the power of pi 2, times h prime. So here, g is pi 1 and h is pi 2. So we have pi 2 prime times the natural log of pi 1 plus pi 2 over pi 1 times pi 1 prime. And so, of course, when I say pi 1, I mean pi 1 of xyz, and when I say pi 2, I mean pi 2 of xyz. So this equals, well, pi 1 of xyz is just x, and this will be y. Pi 2 prime is going to be the vector 0, 1, 0, and then here we have natural log of x, plus y over x times 1, 0, 0. And so this is going to be equal to the vector. So in the first coordinate we have x to the power of y. Well, let's see here. So this x to the power of y, that's just a scalar. We have this vector 1, 0, 0 being multiplied by y over x, and we have to multiply that by x to the y, so we get y times x to the y divided by x. Or another way we can write that is y times x to the y minus 1. Because having an x in the denominator is the same thing as taking the exponent of x and subtracting 1. So anyways, this is the first coordinate. The second coordinate, we get this natural log of x in the second being multiplied by 0, 1, 0, and then we multiply by x to the y. So this is x to the y times natural log of x, and then we get 0. And so just to be sure, what we need is f prime should be a matrix. So if f is a function from Rn to Rm, then f prime should be a matrix which represents a transformation from Rn to Rm, a linear transformation from Rn to Rm. So it should be an m by n matrix. So here f goes from R3 to R. So f prime should be a linear transformation which goes from R3 to R, which means that should be a 1 by 3 matrix. And that's exactly what we see here. And indeed, if you take any like vector ABC, then you could plug the way that you would So this is f prime at a particular point x, y, z. F prime at x, y, z is this matrix, this 1×3 matrix given as follows here. And if you want to evaluate that linear transformation at a particular point a, b, c, then what you do is you just multiply on the right by this column vector ABC, and so you get a times yx to the y minus 1 plus bx to the y times natural log of x plus 0 times c, so that term doesn't get included. And so, so the point there is that this is exactly what we need it to be. We need this to be a linear transformation from R3 to R, and that's precisely what we have here. So this works out. So that's nice as just like a sanity check to make sure that we are understanding everything and that we got an answer that looks like it could potentially be correct. Okay, so now we move on to B. And then, so let's see here. So this is f of x, y, z. I should have written these down beforehand. So this is going to be x to the y, z. So let f1 be x to the y and f2 be z. And this thing that I'm about to do, I don't like the fact that they didn't really go over how to do what I'm doing here. So what we need to do is we need to take the derivatives of f1 and f2 individually. So f1 prime is going to be, well, this is exactly what we did in the previous exercise. So yx to the y minus 1, x to the y natural log of x, 0. And if we do it for f2 prime, well, this is obviously just going to be 0, 0, 1. Because f2 of xyz is pi 3 of xyz, and pi 3 prime is 0, 0, 1. So that's it. Thus, f prime, again, this is f prime at the point x, y, z. This is a column vector, or this is, we first have f1 prime, and then we have f2 prime. So this is going to look like yx to the y minus 1, x to the y natural log of x, 0, and 0, 0, 1. And just to make sure that this makes sense, f is a transformation from R3 to R2, so f prime needs to be a linear transformation from R3 to R2, and so it needs to be a 2×3 matrix, and that's precisely what this is. Okay. Moving along. F of xy is sine of x sine y. So this is sine of pi 1 of xyz, no, pi 1 of xy times sine of pi 2 of xy. So f prime is going to be, we start from the outside and work our way in. So we have sine of this stuff on the inside. So first we take the derivative of sine to get cosine and leave the stuff on the inside. Sine pi 2. And then we multiply by the derivative of what we had on the inside. Sine of pi 2 prime. Okay, so this cosine of pi 1, sine of pi 2, when you plug everything in, when you plug in x, y into the pi projection functions, you're going to get x sine y. And then for here, to evaluate this derivative, we need to take, we need to use the product rule. So we're going to multiply by pi 1 prime sine of pi 2 plus pi 1. Then we have to take sine of pi 2 and take its derivative. Okay, so the cosine of x sine y will stay. Then here, pi 1 prime is 1, 0. Then we have sine of y plus x times, and now we're going to have the derivative of sine, which is cosine at pi 2 times pi 2 prime. And so this is cosine of x sine y times 1, 0 sine y plus x cosine y times the vector 0, 1. And so then this is going to be, okay, so everything else remains, sine y times, okay, so now we're going to combine this into one vector, so it's going to be sine y and then x cosine y. And then we could combine this into one single vector if we wanted to, but I don't really see a reason to do that, so I'm not going to. Alright, let's see. So I have 5 pages of notes on this, and so if I do part D, then we'll be through 2.5 of them. So that'll be a good stopping point, because my computer is not liking all this computation. And perhaps you aren't either. But, oh well. We have to get through this. And once you get the hang of these exercises, they aren't that bad, I don't think. Okay, well, this next one is actually kind of bad. It's pretty intensive, because it's like, from the last one, if you do the last exercise, then you sort of understand the gist of how to do this one. It's just more complicated. I don't think it, like, sheds necessarily any more light than the previous one, but the only way to make sure that you really understand math is to do a whole bunch of exercises, and the more you can do, the better. Okay, so let's just do it again. We got the chain rule, so we have cosine of all this stuff, and I'll just go ahead and write x sine y sine z, because normally we would first keep the projections in there, but there's not going to be any derivatives going on in here. All the derivatives will be going on in the second term that I'm about to write, and so that's fine. So we have pi 1 sine pi 2 sine pi 3 prime. Okay, so this cosine of x sine y sine z is going to follow us around a lot. And we're going to, so now we have pi 1 prime, which is 1, 0, 0, times sine of pi 2 sine pi 3. So we can just fill this in with sine of y sine z, because there's not going to be any derivatives involved in there. Plus, now we keep pi 1, so that's just going to be x. And we multiply by cosine of, and then these things, there won't be any derivatives anymore. And then we have to multiply by the derivative of the inside. So sine of pi 2 sine pi 3, we have to multiply by the derivative of the inside. So the derivative of pi 2 sine pi 3. So this thing gets a derivative. Then we have to close that parentheses. Thank God I was able to fit everything on one line. Not that it's really a big deal. Times, okay, so we've still got 1, 0, 0 times sine y sine z plus x cosine of y sine z, and this thing we have to multiply by pi 2 prime sine pi 3 plus pi 2 cosine, not so sine, that's not a thing. So we have to take pi 2 and multiply by the derivative of sine of pi 3. So that's going to be cosine of pi 3 times pi 3 prime. Okay. Okay, so we have cosine x sine y sine z times 100 sine y sine z plus, then I'm going to go ahead and break this into two terms. So we're going to have x, so the first term we're going to have is going to be x cosine y sine z times sine z, and this whole thing will be multiplied by 0, 1, 0, and then we'll add, here we need to keep that x cosine of y sine z again, because that's being multiplied by the sum. So then we have pi 2, which is just y, cosine of pi 3, so cosine z, then multiplied by 0, 0, 1. And so finally, this is going to give us, so I'll leave this cosine of x sine y sine z on the outside. We'll multiply by, okay, so this vector, the first coordinate is going to be sine y sine z. The second coordinate is going to be x cosine of y sine z times sine z. And then the final coordinate is going to be x cosine y sine z, y cosine z. Alright, so that's this one. It's a lot similar to the previous one, but with more work and not too much of a benefit. But, oh well, here's how you do this. And yeah, I think I'm going to pause this here and then continue with parts E, F, G, H, I, J. Is there really that many left? Yeah. 1, 2, 3. Wow. Alright, we'll finish up next time. So we have completed half of the exercise. Alright, last time on Spivak Chapter 2, Exercise 10, we had a whole bunch of calculus. And now we are just doing even more. So, let's start with f of xyz equals x to the y to the z. So this is pi 1 to the power of pi 2 to the power of pi 3. So, do you remember that formula from before? Because I don't, so I'm going to look at the formula from before to remind myself. Okay, so it's how to take derivatives of one function. It's if your function is a function to the power of a function, how to take the derivative. We're going to be using that here. But we're going to be using it even more. So anyways, f prime is going to be, so you start with what you had at the beginning, so x to the y to the z, times, and so we're going to start on the outside and work our way in again. So in the previous exercise, I had like how to take the derivative of y, where y equals g to the power of h. So here g is going to be pi 1, and h is going to be pi 2 to the power of pi 3. So we start with pi 2 to the power of pi 3 prime times natural log of pi 1 plus pi 2 to the power of pi 3 over pi 1 times pi 1 prime. Okay, so most of the things here aren't too bad except for this pi 2 to the power of pi 3, because there we have to do the entire argument all over again. So we have x to the y to the z times, okay, so this whole thing becomes pi 2 to the pi 3. So I'll just write that as y to the power of z, because that's what it's going to become. And then we do this pi 3 prime times natural log of pi 2. So that's going to be 0, 0, 1 times the natural log of y. Plus, when we take pi 3 over pi 2 times pi 2 prime. So z over y times 0, 1, 0. Okay, so this whole thing is pi 2 to the power of pi 3 prime. And then we can just add in everything else. So we have natural log of x plus y to the z over x times 1, 0, 0. Is that all the parentheses? I think that's right. Okay. So we have x to the y to the z. Then here we've got can we just go ahead and I think we can skip right to the end. So in the first coordinate we have y to the z over x. The second coordinate we have z over y times the natural log of x on the outside. But we've also got that y to the z. So we have y to the z. So we have that z, and then we have y to the z over y. So that's going to be y to the power of z minus 1. Then we also have natural log of x. And then finally we have natural log of y, natural log of x, 0, 0, 1, y to the z. So we have y to the z, natural log of x, natural log of y. And that's it. So I guess this didn't turn out too bad, but it's a little annoying that we had to apply that exponent rule 2 times. Alright. So now that we've had to deal with the case of that, okay, well here we actually don't need to do that again. Okay, so f of x, y, z is going to be x to the power of y plus z. So that's pi 1 to the power of pi 2 plus pi 3. Okay, so f prime, of course this is f prime at x, y, z. It's going to be, well, we start with the beginning x to the y plus z. Then we multiply by pi 2 plus pi 3 prime times natural log of pi 1 plus pi 2 plus pi 3 over pi 1 times pi 1 prime. So this is going to be still x to the y plus z. Now here we get this vector pi 2 plus pi 3 prime. Remember, derivatives commute with addition, just like we would expect from intro level calculus. So this is 0, 1, 1, because it's 0, 1, 0 plus 0, 0, 1 times natural log of x plus y plus z over x is 1, 0, 0. So what we end up with is we have x to the y plus z on the outside. Then we've also got y plus z over x, natural log of x, natural log of x. And that's it. Alright, so that's nice. This next one, that took 4 lines. This will probably take 4 lines as well. We have g. Will it take 4 lines? We'll see. So this is f of x, y, z, similar, but except it's not. It's x plus y to the z, which is pi 1 plus pi 2 to the power of pi 3. So f prime is going to be x plus y to the z. Of course, we keep that on the outside. And we take pi 3 prime times natural log of pi 1 plus pi 2 plus pi 3 over pi 1 plus pi 2 times pi 1 plus pi 2 prime. Okay, so we got x plus y to the z. We've got 0, 0, 1, natural log of x plus y plus z over x plus y, 1, 1, 0. So at this point, hopefully this is starting to become a little more straightforward. We're starting to do a lot of the same sorts of techniques over and over again. Z over x plus y, z over x plus y. Then we get natural log of x plus y. Does that agree? Yeah, that agrees with what I had. Okay, cool. All right. Moving along, we've got h. F of xy is going to be sine of xy. So that's sine of pi 1 times pi 2. So f prime is going to be, we use the chain rule. So we get cosine of pi 1 pi 2 times pi 1 pi 2 prime. So this is going to be cosine of xy times pi 1 prime pi 2 plus pi 2 prime pi 1. So this is going to be cosine xy. Then we've got 1, 0 times y plus 0, 1 times x. So we get cosine of xy times the vector yx. So it sort of reverses order. Alright, now we're finally on the last page here. Oh, this video is actually going a lot faster than the previous one did. I wonder if I could even combine them into one video. I might do that. F of xy, well, I'm sure you will know if I have done that or not, because by the time I'm uploading it, I will have figured it out. Okay, so this is sine of xy to the power of cosine of 3. Cosine of 3 is just a number, so this is not going to be, it sort of looks a little weird, but because it's just a constant, it works out really nicely with differentiation. Okay, so we have sine of pi 1 pi 2 cosine 3 in the exponent. So f prime is going to be, we put it on the outside, and now the first thing we do is the first term is going to be cosine 3 prime times the natural log of sine of pi 1 pi 2. But cosine 3 prime is 0 because cosine 3 is just a constant. So taking the derivative of a constant is 0. So that term completely drops out. All that we're left with is the second term, which is cosine of 3 over sine of pi 1 pi 2. Then we have to multiply by the derivative of sine of pi 1 pi 2. Okay. Oh, but we did that already. So that's nice. Cosine of 3. So I'm going to do this again. So we have sine of xy to the power of cosine of 3, and we're dividing by sine of xy because we're dividing by sine of pi 1 pi 2. So I'm just going to put cosine of 3 minus 1. This is not cosine of 2. We're just subtracting 1 from the exponent to account for the denominator. Then we multiply by cosine of 3, and then we just multiply by the answer we got from h, which is cosine of xy, and we have yx. And then finally we're on to j. And j is just a combination of a whole bunch of the previous ones. So we've got f of xy equals sine of xy sine of x sine y and x to the y. And so the first one, this is part H, this is part C, and this is part A. So we just combine them into a matrix. Remember, F goes from R2 to R3, so we need a matrix that goes, we need a transformation which goes from R2 to R3, so it's going to be a 3 by 2 matrix. So we're going to write it like this. So in the first column, we're going to have the derivative of sine of xy. So it's going to be y cosine of xy and x cosine of xy. Because remember, in H, the answer was cosine of xy times the vector yx. So the first coordinate is y cosine xy, second coordinate is x cosine xy. Then for C, if you go back, you'll see that we had sine of y cosine of x sine y, and then we had x cosine y cosine x sine y. And then finally we had y x to the y minus 1 and x to the y natural log of x. And this is our matrix. And again, if you plug in any point A, B, and C in R3, then you write that as a column vector here, and you do... No. This needs to be a transformation from R2 to R3. So you take a vector A, B, and R2, write it as a column vector, multiply it by on the right by f prime, and this gives you a column vector in R3. So this is indeed a linear transformation from R2 to R3. And so yeah, this is how you do derivatives using the techniques of this section. And by the way, no one does this. This is all stuff that we have to do because of the tools that we have at our disposal. What people actually do when they need to find the derivative of a function from Rm to Rn is that they use partial derivatives, and we're going to learn about that in the next section. So once we learn that, we can sort of take all of this stuff and sort of throw it away and never really use it again. I guess it's useful to know that you can do things this way, but in general it's going to be much easier to do things using partial derivatives. And it will make, like, a lot of these computations that we did here are really messy. If you do it in terms of partial derivatives, things work out much more nicely. And so, yeah, we will talk about that more in the next section. But for now, we are done with this exercise.